I'm Joe. Today we're going to learn to write a prime number calculator using Python. So we want to be able to calculate all the prime numbers up to a number given by the user. Let's call that n. So let's start with a definition for prime number. A prime number is a positive integer that is evenly divisible only by 1 and itself. So all the prime numbers under 30, 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And as you look at each of these, you can see that each of them is divisible only by 1 and itself. And prime numbers exclude the number 1. So let's take an example, 9. How do we determine if 9 is prime? Well, we have to start at 2, and we'll count up to 8. And we want to divide 9 by each of those numbers, one at a time, and see if we get a remainder of 0. Right? Because if we get a remainder of 0, then it's prime. So 9 divided by 2 is 4 with a remainder of 1. 9 divided by 3 is 3 with a remainder of 0. So that right there tells us that 9 is not prime, because we got a 0 remainder, evenly divided by 3. 9 divided by 4, 2 remainder 1. 9 divided by 5, 1 remainder 4. And we can finish out these calculations. But the only thing we're really interested in is the remainder. And in the case of 9, 9 divided by 3 is the number that tells us that 9 is not prime. So since we're only interested in the remainder, what Python function can we use to do this calculation? That's right, the mod function. So in case you're not familiar with it, hopefully you are, but the mod function gives you the remainder of a division. So 9 mod 3 will give you 0. 9 mod 4 will give you 1, the remainder after the division is done. So if 9 mod y is equal to 0 for any y in the range 2 through 8, then 9 is not prime. That's how we can determine if 9 is prime or not. That's basically what we just did. We modded 9 by each of the values from 2 through 8 to see if any of them are 0. So how can we put this into code? Well, we're going to start by assigning 9 to x. X will be the number we're trying to determine if it's prime or not. We'll use a Boolean value, is prime, and we'll start out by assuming that 9 really is prime. So we'll say is prime equals true. Then we have to use a for loop for y in range 2 through 9. Now bear in mind this 9 here is only going to count up to 8 because the range function does not include the 9. It uses 9 minus 1. So it's going to use values 2 through 8. So if x mod y is equal to 0, then is prime is equal to false. In other words, we're going to set this is prime flag to false if we find that our x value is evenly divisible by any number in this range. Okay? We're going to basically do this calculation for each number in this range, set is prime to false if we find a number where it is evenly divisible. So that is the simple prime engine, the standard engine for calculating if a number is prime or not. And what we're doing is just repeating exactly the same calculations using our Python code. It's exactly the same calculations that we did here. So back to our code. What if we wanted to find all the primes up to 10? With two simple modifications, we can find all the primes in a range of numbers instead of just determining if a single number is prime. So first we want to say for x in range 2 to 11, again, remember, this 11, Python is only going to go from 2 through 10. It does 11 minus 1. And the other change we need to make is for y in range 2 to x, which is actually going to use x minus 1, which is what we want, right? So if x is equal to 9, we will be looking at values 2 through 8 for the y values. And that's it. So these modifications to our program will tell us if all the numbers from 2 through 10 are prime or not. Now if we wanted to find all the primes up to a maximum number, let's say a user entered value called max. That's easy enough. We're just going to change the x value to max plus 1. Why max plus 1? Because again, the range value goes 2 through 1 minus this. If 2 through 10 are prime, then we have to add 2 through 11 in the range function. Now we're ready to get user input for a value called max, which we can plug right into our prime engine and calculate if the numbers 2 through whatever the user entered are prime or not. We have a nested for loop to do all that calculation. So our nested for loop, this is a standard construct in computer programming. An inner for loop that does the work, right? It's doing a calculation. In this case, we're using y for our inner loop variable, and we have a range from C to D. And then we do stuff internally. We do a calculation. And then we have an outer loop that cycles through a value that we're doing this set of calculations on each value in the outer loop. So this is known as a nested for loop. So now we've taken that code and inserted it into our text editor. We save this as a primes1.python file. And you can see on the top we added a line to get a max value from input from the user. And at the very end of the outer loop, inside the x loop, we added a print statement to print x if x is prime. So let's see if this runs. So let's find the primes up to just say 100. Boom, it's pretty quick. But when we search for the primes up to 10,000, it's going to be a lot slower. Quite a bit slower. Still chugs through pretty fast, but we can see that there are a lot of print statements. It's printing each number as it goes. And we're also doing a lot more calculation than we need to, as you'll see soon. So we're going to optimize this program, make it a lot faster. So here's our code again. And we can see that the program really doesn't need to do any calculations beyond 9 mod 3. Because at this point we find that 9 mod 3 gives us a remainder of 0. So we already know that 9 is not prime. So there's absolutely no benefit to continuing with the rest of these calculations down here. So by adding a break statement into our inner loop, if we determine that a number is not prime, we can avoid doing a lot of additional calculation. That will make our program a lot more efficient. So here's our second version of the program where we added a break statement if we find that a number is prime. So that it'll stop calculating and exit the inner loop if we found that a value is prime. So let's run program 2 and see how that works. We'll run it with a value of 10,000. We can see that runs quite a bit faster than the previous version. Now what if we wanted to save those prime values that we calculated to a list? First, why would we want to do that? Why would we want to save these prime numbers to a list instead of just printing to the screen one by one? Well, for one, it's a lot more efficient. Because if you're calculating all the prime numbers from 1 to 1,000,000, you have 1,000,000 print statements, which is going to slow down the speed of your code. And for 2, you haven't saved those values anywhere, so you can't use them for any future calculations. If you need access to that list of primes, you have to save them into some sort of a list. So here we've implemented a list, and if you're not familiar with lists yet, don't worry, we'll have a future video to cover lists in detail, but right now this is a very basic application of lists. It's going to be pretty simple to understand. We set up a list called prime list. We made it an empty list using these square brackets, and then each time we find a value that is prime, we simply append it to our list using a .append function. And then when we're done with both loops, the whole program is done running, we have prime list, which is a list of all the found prime numbers. Now let's look at our third update of the program, where we're using a list to save the values to it. So the list version of the program runs very quickly, and it prints out all the numbers in one single print statement. The 10,000, up to 10,000 took only a matter of a few seconds. So how can we make the program even faster? Well, let's look at a number 48, and let's look at all the factors for 48. So if you start at 1 and look at all the factors for 48, 1 times 48 is equal to 48, 2 times 24, 3 times 16, 4 times 12, 6 times 8, and so on. Something you notice after 6 times 8 is that these are really all the same on the right-hand side. When you reach 6 times 8, 8 times 6 is really exactly the same two factors, just in reverse order, right? With the bigger number first. So really, we see this tipping point happens at the square root of 48, which is about 7. So there's really no need to check for primeness after the square root of a number, because after that you're just duplicating the effort. So the way to speed up our code is by stopping when we reach the square root of a number. So for instance, let's look at a big number where there's going to be a lot of calculation involved. The square root of 999,979 is about 1,000. 1,000 squared is 1,000,000, right? And this number is just under 1,000,000, so it's just under 1,000. Doing mod calculations for up to 1,000 alone is sufficient to determine primeness of this number. But if we continue doing calculations all the way up until n minus 1, 999,978, we could have stopped at 1,000, and we've done 1,000 times more calculations than we need to. So we can make our program way faster for large numbers by simply stopping when we reach the square root of the number. And the modification to the code itself is really simple. All we have to do is, for the outer loop x, we want to take the square root of x, or by raising x to the 0.5 power, the 1/2 power, that gives us the square root of x. We'll take an integer value of that, since it very well may come out to a decimal value. We'll convert that to an int, which rounds it off, and then we'll add 1 to it. That simple modification will substantially improve our performance when calculating primeness for very large numbers. Now let's look at the newest version of the program where we're stopping when we reach the square root. That prints out almost instantly, so let's try 100,000. 100,000 also prints out almost instantly. So you can see with a few edits to our code, pretty small changes, we've actually improved the speed of the program considerably. This shows how the performance compares between the 4 different versions of the program we wrote. So I did a time comparison calculating the primes up to 100,000. The first version of the program took 23 minutes. Just by adding the break statement in version 2 of the program, we got the runtime down to 2 minutes and 2 seconds. We were able to shave off another 5 seconds by using a list instead of printing each one as we found it. In version 4, we used the square root to cut off the number of calculations we were doing, and this brought our runtime all the way down to about 1 second. So with some smart program enhancements, but not a lot of code, we were able to reduce the runtime from 23 minutes down to about 1 second. I'm Joe James. Thanks for watching.